Okay. Hello, everybody. Let's just start. Sorry for the delay. I've been struggling with this screen sharing. Apparently, it doesn't work after the new version of the OS on my iPad. So if you remember, we discussed about gradient ascent in the last lecture, and it was a very simple procedure for optimizing the type of classifier that started with. Basically, we discussed about binary classification and multi-class classifiers. And this gradient ascent was a way to find optimal parameters in order to give us the right model that provide a decent classification based on our training data. And the idea was very simple. We started by a random initialization in a space of the weights. Right here, we have two dimensions here, x1 and x2. We initialize from somewhere, and we follow the direction of the gradient. So it is an iterative approach. In the first step, we calculate the gradient at this point, and then we find the next point in this space of weights, and then we do the same procedure. At each point, we calculate the gradient with respect to the current point in this space, and we follow this iterative approach, and we repeat it until we converge somewhere, and we call it done. So it is very simple approach. We discuss it in detail, how it looks like, and what are those reasonable stopping point then when we can call it done. Do you have any question about this? I hope you can hear me well. And then we discuss about this idea of why taking the steps toward the gradient is a reasonable or the optimal choice here. We discussed about if we have a constraint, so in this case, can you see the right slide here?
I'm looking at the gradient descent slide, the one with that shows the concentric like ellipses.
Why it was not updated? Let me see. It's weird. So here we are given a specific function. I'm not sure why it still is not updating the slide. There's something wrong.
Is this supposed to be showing all the formulas right now?
Yeah, you don't see it, right?
No, I just see like the bottom right corner. Like I see delta G equals like the partial derivatives, but that's it.
Yeah, I'm not sure what's going on. Let me see. Let me see how can I fix it. Sorry about that. now seems to be working. Let's see. So, okay. So we discussed about this situation where we are given a function g here, and we have a constraint. So we can change the weights. So w is the input for this function, or it's a weight, and we can move or change weights according to a certain constraint. And then we expanded this g w plus delta according to the first order Taylor expansion, and you know that in this case you can change g here. When you are given a delta here, you can expand it based on g of w, the initial weights, plus the amount of change according to the first coordinate of delta 1, multiplying by the gradient of g with respect to the w1, and the second coordinate of delta 2. Delta is basically the amount of change that you are adding to the w, multiplying by gradient of g with respect to the second coordinate of the weights. And then we looked at the steepest ascent direction. So this is, we want to maximize, because that was our goal. We wanted to maximize amount of g, the target function, when we make a change to the w. And then we know that in calculus, when we have a direction, and we know by default when we want to maximize the inner product between two vectors, we better to align them completely together. And this is the way how we can make this alignment when we have this constraint with respect to the amount of change we want to make according to this. And we can, based on the construction, we can do the same. We can, here in this case, A is this vector. So we can construct this vector, and we know that by construction, this is the steepest direction in the basically for making the change in the weight vector. So basically, gradient ascent give us the right direction to move forward, and that's the proof by construction why this algorithm gradient ascent or descent, depending on the target function, makes sense and give us the right direction to move iteratively. Do you have any question about this? So that was basically showing why gradient ascent makes sense and why it is making the right direction at each iteration of the algorithm. Okay, now I need to learn how to remove these annotations. And if we want to do that for the functions with larger number of dimensions, for example, in this case, n dimensions, we can do the same. So basically, the gradient is a vector of n dimension. It's very similar to 2 dimension, and we can do the same procedure as we move forward according to the algorithm. So in this case, we have a very simple iterative algorithm. We initialize the weights, and then we have a loop to infinity Obviously, we need to stop somewhere. We discussed when we can stop, or when it makes sense to stop. We add to the initial weights based on the learning rate, which could be a small amount, and multiplied by the gradient of our objective function, g of w, at each point in the space of weights. So this is very simple procedure, and for choosing the learning rate, we discussed that this is a reasonable choice, a very small amount. This learning rate could be fixed or could be also adjusted during the learning. Typically, there are algorithms and extension of gradient ascent that update the learning rate according to a simple rule. As we get closer to the target value, to the optimal value, we make alpha, the learning rate, smaller, because we don't want to jump around the optimal point in the weight space. So this is a rough estimation about what kind of value we need to consider for alpha in this case. So roughly at most 1% of the function value in this case. Any question about this algorithm? So this gradient ascent is an optimization algorithm that could work for any optimization, any maximization or minimization that we have. For classifier, we know that the function g in this case is likelihood of the labels given the input and the weights. We discussed extensively about this log likelihood. We want to maximize this log likelihood in order to give us the right prediction, at least for the training set that we have. And this is sum over all training examples. So we have a set of examples, x1, y1 plus x2, y2, xn, yn. So these are given. So these are, you can represent it as D, your training set. These are given to you. So you know what are the ground truth data. So you know the yi's, and you can calculate this probability for all training examples that you have in D. D again is your training set. Typically, you want to split your training sets into two different sets. You want to use one set for using in this procedure, and another set held out data in order to check when it makes sense to stop. And we discussed that, how you can make that decision in the previous lecture. So again, we do really the same procedure as you know in gradient ascent. You start by an initial weight, and then you plug in this function into your procedure. For each step, you take one example, you select one of these, you plug it in here, and then you calculate the log likelihood of the labels given the input and the current weight that you have. And you need to know that this is, again, this weights is updated. So for the next examples that you select, you're calculating this log likelihood on a new weight. So basically, when you started by W0, the next step, when you calculate for the second example, you calculate the log probability of the second example, in this case, y2 given x2 W1 in this case. So in the previous one was differently. The previous one was the log likelihood of probability of y1 given x1 and w0. So make sure that you understand the difference. The condition part was different in terms of not only the example that you used, but also the weight that was used previously. So these are the two essential differences in this update rule for the weight. And at each iteration here, according to this, you select one example at a time, and you make the update to the weights. Do you have any question about this?
Yeah, I was just wondering, why log? Why log likelihood?
Yeah, that's a very good question. This log likelihood is mainly a mathematical trick. So it's for convenience when you want to do this optimization. Essentially, you could do calculation based on only the conditional probability, but this log likelihood, when you want to calculate the gradient, it makes it simpler in your optimization procedure. So it's a mathematical convenient transformation, and in calculus, in other form of mathematics, these kind of transformations basically make these calculation a lot more convenient. What's going on here? Do you see the slide or not?
No, I see the slide. I'm not sure what you're talking about. Like as in like what's going on. Are you seeing something different, or oh, now I'm seeing
something
formulas. I'm seeing the formulas disappeared, or half of them anyway.
Yeah, I'm not sure what's going on.
Oh, we're back on the original slide now.
Okay, very well. So basically, this log is mainly out there for making the calculation of the gradient a lot simpler in the optimization process. I hope this makes sense for now, but consider it as a mathematical trick. Any other question? Very well. Okay, now you may want to think that maybe if you have so many examples, so many training example, sometimes, and in most of the cases, if you think that you might be able to do a lot of these calculation in parallel, maybe then you may want to take advantage of these parallel computation that you have. Sometimes you know that, like, instead of calculating the gradient with respect to all examples that you have, you may want to pick a few examples and then calculate the gradient with respect to these few examples in your training set. And then next time, when you want to make a change, update to your weight, then you pick another set of random examples and you do the same procedure again and again. So this is called a stochastic gradient ascent or stochastic gradient descent. And the reason why we call it the stochastic here is that instead of calculating this log likelihood or gradient with respect to this conditional probability for all examples in your training set, you pick some random examples at each iteration, right? So at each iteration, you pick some example depending on the amount of compute that you have. For example, imagine that you have 100 GPU cores, then you want to calculate all of this in parallel. Then you can pick 100 example, you calculate this conditional probability, although this is not the exact gradient because you haven't used all example in your procedure, but this gives you a noisy version of the gradient, still useful as a signal, and you want to make the update to your weights according to this noisy estimation of the gradient that you have. And for the next point, so imagine here you started from W0, you selected 100 example, and this 100 example give you an estimate of the gradient. Now here your W1, then at W1 you select another random set, right? And then basically you do the same procedure again and again, right? So at each iteration, you select a different set from your training example in order to calculate this log probability, even though the gradient estimation is noisy, but it's still useful, and this algorithm still has the convergence property if you make sure that you select these examples in a really random way, and there is no correlation between the examples that you pick at each iteration. Do you have any question about this? So this is very similar to the standard version of gradient ascent, but we call it the stochastic because instead of using all example in your training set, you select a batch of random variables or few, depends on the number of the number of compute that you have. If you only have one, for example, core, maybe you want to use only one example. If you have multiple core, you want to use more number of examples from your training example, right? So it really depends on the amount of compute which are given to you. And you can vary this mini batch differently, right? Could be as small as one example, could be as large as the whole training data that you have. So you have, this again really depends on the amount of compute that you have. You can make this procedure a lot faster. Obviously, if you, so there is a trade-off here going on. If you select this batch larger for this procedure, you calculate this gradient obviously more accurately. If you select the smaller batch, this calculation would be noisy, but would be a lot faster. So you have a trade-off between converging faster, or you want to pay off more compute here to get calculation more accurately. But obviously you need more compute, and you may need to have to use more compute here at each iteration in order to do this optimization procedure. So the selection of this mini batch, the size of this mini batch matters, and this really depends on the amount of compute and the amount of noise that you can afford for this calculation. Now that we have learned about this optimization procedure, we know how to optimize a multi-class regression model. Right. So now we know how to optimize this multi-class logistic regression. We want to extend it to a neural network. How to do that? This is really simple, and that was the key reason that we started by this multi-class logistic regression, to build the intuition behind neural network. We could have started well by simple version of neural network, but this way you can see that neural network are a special case of logistic regression, where the set of features that you use in your model are given. In this case, so you have a set of feature, and then you have a set of activation, ZI. Each ZI is a weighted vector of the features. So for example, W1, W2, right, WN. So this inner vector of W by your feature vector is basically is the activation that that you can get here, right? So you calculate the activation based on the given feature values. We discussed this extensively previously, and then you pass it through a layer softmax in order to calculate these probabilities. So again, to repeat here, these activations are not probability distribution. These are real numbers from -infinity to positive infinity. The reason we did this transformation was again make it mathematically more convenient in order to give us the flexibility of distinguishing between different, for example, classification, right? So we discussed this case where we have different example, right? Positive cases, right, and negative cases. We might have different decision boundary, right? This is one decision boundary. This is another decision boundary. Both of these are correct. This is also the third, fourth. We might have many decision boundaries here to choose to classify these two sets. Without such transformation, without having these probabilities, it was impossible for us to distinguish between these different decision boundaries. And we discussed after doing these transformations, since we have these conditional probabilities, then we could reason about what conditional probabilities give us the highest likelihood of the data, at least for the training sets that we have. So with this reasoning based on probabilities, we could reason about the goodness of these different decision boundaries, and then we could pick up the best one according to this. So we have this softmax transformation where we use these activations. Here we assume that we have three activations, Z1, Z2, and Z3, and then with this simple softmax transformation, we get this probability distribution. Any question about this? The important thing that you need to know in this logistic regression that we discussed is that these feature vectors are given to you, right? You started by assuming that we know what are these feature vectors. And the learning part here was to learn these weights, right? So we did not wanted to learn these feature vectors. These feature vectors were given to us. We just wanted to learn these weights that maximizes these conditional probabilities after we do this softmax transformation. So these probabilities somehow were connected by with these weights. So obviously with different choice of weights, these conditional probabilities would be different. And when we sum over these P, yi given xi and wi's, this sum would result in different value, and we wanted to select the strength of this link that make this sum maximal way, right? So this log likelihood, we wanted to maximize this given the training examples that we have. That was really the mechanism or the mechanics behind this learning procedure that we discussed. Any question about this? So now, since we know this multi-class logistic regression, then turning it to neural network is really simple. And the question is that, can we, instead of assuming that we know this feature vector, can we learn these feature vectors as well? And the answer is that yes, you can. And then you need to think about what are given to you and what needs to be learned, right? So you can assume that you have some magics here. Obviously, you have some input, and these inputs are already in your input vector, your x, right? For example, if you have an image, you know already this x value. For example, is x1 to xl could be pixel value in your image, right? So in a digital image, you have different pixel values. These are already given to you. You see what is the strength of each pixel in your image. For example, any value between 0 and 256. You can extract this. So assuming that you know this x1 to xl is obvious, and then you need some magics to transform this pixel value to some feature vector automatically, obviously, instead of handwriting it. And then the rest, you already know how to do that. So in traditional machine learning, you write program in order to do this transformation for you. For example, you look at the image and you count how many loops you have, how many edges you have in your image, how many maybe corners you have in your image. So you count the number of, you calculate the important features by writing some programs, right? So you need to do some calculation, and these calculations are really based on the intuition that you might have. What are the important features that you might have? So you write some program to do this transformation from the raw data, the raw input, to some higher order representation in the input space. With neural network, we would like to learn this program using the data, and that's the key difference between traditional machine learning and neural network. You might have heard about software 1.0 and 2.0, and this is essentially the difference between two. In software 1.0, you write programs such as C++, Python code, or something like that that transform these features into, transform these inputs to your feature space by writing explicit programs that exploit the knowledge inside your head, what is important for this learning task. In software 2.0, you just use a magic, a black box that we will describe shortly, in order to only use your training example in order to learn that program. So you learn this program instead of explicitly writing this program. I hope it does make sense to you. And the way how you do it in neural network is really through some, again, repeating the same sort of transformation that you saw here. So here you have some transformation going on from your feature space to your activation. You repeat the same, but now multiple times. So you have different layers. You start by your input, which are already given to you, and then you repeat this transformation several times, depending on the depth in your network that you want to get. So obviously, if you increase the depth, maybe this magic become better somehow. If you decrease the weight, the depth of your network, maybe this magic become less effective, or it becomes simpler, right? So it's really a set of transformation that you do in order to transform your input to these features, and then the rest you already know. And here you have again similar thing. Think about each of these ZI, again very much similar to these two things, but now so each of them represents a set of features, but with different complexity. But for now, again, each of these links represent weights, so they have a different strengths. So each ZI here is a weighted sum of the previous example that you, the previous input that you have, right? And then you calculate this inner product between the input and the weight, and you pass it through some nonlinearity in order to transform this each layer to the next and next and next until you get the right feature vector in the last layer. Then you can transform it to your activation function, and then you can calculate this conditional probability. So we repeat the same procedure several times with the hope that that we get the whole end-to-end network correctly. So here again, some mathematics, linear algebra, in order to make a sense out of it. So you have some weights. So in order to calculate the activation for layer K, right, and each of them are indexed over I, you need to have the weights for, you need to have these weights that connect the previous layer, the nodes in the previous layer to each of the nodes, to each of these ZIs, and then multiply it by the activation in the previous layer, right? So for example, for calculating this guy, you need to have each of these activation that belongs to the previous layer, right? And each layer here, so here, for example, you have how many? You have K one number of nodes. Here in this layer, you have K two number of nodes, and these could be different, right? Maybe here you might have 10 nodes, here you might have 100 nodes, and differently. So you might have different neurons or nodes in the network at each layer. So for calculating this guy, you need to have these 10 activations, for example, and you need to have some weights associated to this, and the weights again is a similar notion. Determines the strength of this connection. If a weight is higher, means that this connection is more important, more values going from this node to this node. and if the node is this link is thinner, means that the connection is less important, right, comparing with the other connections. And then you pass it through some nonlinearity in order to calculate the activation for each of these nodes. And the reason that you need this nonlinearity is very simple. If you do not use this nonlinearity, this inner product between the activation and the weight vector is linear, so it keeps everything linear. And if we have a linear function and the data in your training set is not linearly separable, this doesn't work. Like whatever number of neurons you want to use, whatever number of layers you want to use, as long as you don't have this nonlinearity, this transformation stay linear. So if you add millions number of layers, since this calculation is linear, everything will stay linear. And if your examples are not linearly separable, then even such complex network cannot classify your examples properly. So you need some nonlinear transformation in order to make it to make this happen, to make this separation between nonlinear example happen. Any question here? So again, a very simple extension of multi-class logistic regression, transforming it to a deep neural network. So it's deep neural network are not really magic, simple extension of what we already know in multi-class classification. So some of how this nonlinearity looks like, right? It's very simple. We have different functions like sigmoid function, hyperbolic tangent, ReLU function, and so many other type of nonlinear function with different type of transformations, right? So again, for example, in the sigmoid function, you see that we had this sigmoid function before for transforming for using it in multi-class logistic regression. So it has a very simple formula, and the gradient of the sigmoid itself is very simple to calculate. So it transforms the input from minus infinity to positive infinity between 0 and 1, right? The hyperbolic tangent is centered around 0. So as you go to positive infinity, get closer to 1, the other way around, get closer to -1. Instead of 0 in sigmoid function. And in ReLU is a simple switch on and off. Everything negative will be turned off, and everything positive, you use the same value as your input space, right? The calculation is really simple. And that's why it makes sense to use ReLU in neural network, because first of all, calculating this transformation requires less computation as opposed to hyperbolic tangent and sigmoid. In hyperbolic tangent, you need to calculate exponential of Ez and E minus C. In sigmoid, only E minus C. Here, you do not need any calculation. You either switch off, you use 0, or if it's positive, you use the same value. So no calculation, is just only checking whether it is positive or negative. Is the if then kind of code. One line of code, you can calculate GZ, and it's basically for calculating the gradient of G is so simple. So is either 1 if this is positive, or 0 otherwise. There are some certain reason why someone might prefer a ReLU function over other type of activation functions in this case. Any question about this?
I had a question. Is there any reason someone would choose the sigmoid or hyperbolic over the ReLU function? Because I mean, I see that I'd read something about the ReLU function avoiding something called the vanishing gradient problem. And so I've got some vague understanding of what that is, but I also see that it's easier to compute. So I was just wondering if there was any advantages of the others.
Yeah, there are some reasons, right? So you see that, for example, around 0, the gradient of this function, hyperbolic tangent, you can calculate it, right? Here is also the same, right? But for this, right, you have you have right-hand side or left-hand side gradient, but not exactly in 0, right? So you have this property of ReLU that causes, for example, this vanishing gradient in the optimization. So you have some trade-off for these choices, right? It really depends on a type of data that you have, on a type of optimization that you have, whether this is, for example, you're classifying images or text or some other task, right? So you may want to prefer one activation over the other, or the amount of computes that you have. So there is a trade-off space here, but it really depends on the classification problem, type of data, and the amount of compute that you have. There is no hard rule for each. Typically, people, they start with some default choice, right? ReLU. If that doesn't work, then people may try different choices of activation function, whether they get better accuracy or better generalization on different tasks. I hope this answers your question.
Yeah. So you select activation function by graduate descent. I don't know if you had heard that joke or whatever, but graduate descent.
Graduate descent, yes, yes, yes. Yeah. Yes, exactly. So it's a yeah, again, it's a simple try and error, right? There is no hard rule for this choice of activation function. That's right. Okay. So let me see. I think we can stop here. But something to mention about neural network is that we have this universal function approximation. This is a well-known theorem that there is a proof of any neural network, any even two-layer neural network. Two-layer means that you have some input, you have one hidden layer, and you have output, right? So basically, you need to at least have one hidden layer here. And in this theorem, basically, the only variable that you have is the amount of neurons that you use in this hidden variable, right? You can increase or decrease, and this theorem says that if you have a function and if you want to approximate it with a certain accuracy, right? Then there exists such neural network that can approximate this function with any desired accuracy. What it means, it doesn't tell you how many neurons you should use, right? So this theorem is not practical in the sense that it doesn't give you at all how many neurons you need for approximating this. The only thing that it says that there exists such neural network. Go and find it, right? So, and that's why it's not really a useful theorem, or it's not an actionable theorem, but is a theorem that you can approximate any function to any desired accuracy, even with this simple neural network, as long as you use enough number of neurons. And maybe let's look at one example here. Right, there are some papers about that, but this, let me see. Let me share this with you. This playground is really useful to look at it. But I'm sure you look at this before as well. But let's play around with it together, because this is cool. Do you see this playground now?
Yep.
Okay, cool. So this is very simple and very cool. Let me see what we have. Right, let's start very simple. We have two input, x1 and x2, and this is very simple data that is linearly separable, right? You can choose your learning rate, you can choose your activation function, you can change it to linear, any regularization if you want to use. You can change your batch sizes. Batch sizes, again, is what we discussed today. The number of examples at each iteration of your optimization. You can change it to 1 or all the way to the number of examples that you have. And then you see that for this linear kind of this data set that we have is linearly separable, right? So even a very simple linear model. So you see that this activation that we use is linear. So you see that this model was able to find a decent model to classify these examples. Well, for example, if you change the data to something which is not linearly separable, then this linear model probably doesn't work, right? So you see that there is no, in this case, the model is not really converging, or as the training goes on, the probabilities over the classes are equal. So the model is not really confident how to classify this example. And most of the cases, when this is the situation, when you saw in your model such situation, you should peek inside and find out the reason why that was the case. And most of the cases, there is something wrong with your model. And you see that even as we train this model for millions iterations, nothing will change. And simply this tells us we don't have enough nonlinearity in the model to separate this, because we know that we need a nonlinear decision boundary in order to classify this training example. But let's try it with different sort of model when we add a kind of hidden layer. Then let's assume that we want to use a linear activation function. By default, we discuss, okay, if we even have numerous number of layers, let's try it with this simple, right? This probably should not work, because we use linear activation, and if we increase the hidden layers, right? See, nothing will change. Still, the model is not giving us a reasonable model in order to classify these examples, because even if we increase these hidden layers to many, and even if we increase the number of neurons to many, since we use linear activation, the model is not giving us a decent decision boundary to classify this, right? This was connected to the reason why we need this nonlinear activation, something beyond linear, right? Why we need ReLU, tangent, or sigmoid in order to classify this, right? So let's try, for example, a simpler, right? So this model is very complex, right? And if you peek inside each neuron thinks very differently from the other neurons, how this classification should work. Let's make it a lot simpler, right? Instead of very complex, let's use something like this, right? Very simple, but instead of linear, let's use sigmoid, right? And then you see that the model start to giving us a reasonable decision boundary. you see that the decision boundary in this case is nonlinear. Obviously, we need some nonlinearity in the model in order to classify this example, right? So we can obviously change sigma to ReLU. See that still it would give us some decent decision boundary to classify this. Still model useful, looks different, generalizes differently with ReLU function, but still is able to classify this example, right? Let's increase the number of neurons like to 6 and do the same. One thing noticeable in this case is that you see that with 4 neurons, you had, so if you look at these weights, right, look at the values of these weights, right, 1.6, minus 1.6, minus 1.6, 1.7. But you have some smaller weights, right? Even though these are useful, but when you decrease this to 4, see, you have different weights. Maybe in this case 3 neurons might be enough, right? See that these values are somehow closer to each other, right? Still, you see that this model is not able to distinguish between the 2 classes that you have properly, but maybe something this is too much for the model, and these are reasonable way that you can think about how you can have different model that gives you different accuracy as well as different simplicity and generalization power for different type of task, right? You can obviously change this to different activation and do the same procedure. You need different number of epochs. Each epoch represents each different iterations that you need to go through your optimization procedure that we just learned today, the stochastic version, right? And you can change the batch sizes and do the procedure until it converges, right? Do you have any question about this?
None here, but I guess I was just going to mention how that does answer my question about the selection between the activation functions.
Yeah,
clearly the tan H or the hyperbolic tangent is better than the ReLU here, by a little bit anyway.
Yeah, it depends. It depends what do you call better, right? For this data, might be the case as long as your testing example would stay similar and you do not observe any distribution shift between your training and your testing, right? But yes, there are certainly some inherent characteristic in your activation function that makes the difference in convenience in your training and optimization, as well as your generalization over your testing examples. And this is a cool tool. You can select different complexities. So obviously this example, like this example is very complex, right? So you see that how complex these examples are. Maybe this model would not be sufficient to learn this train a model reasonable well enough to classify these, right? So you see that this doesn't work, right? So it stucks there, and it is not giving you a good classifier to do the task for you, right? Even if you change your activation to something different, see, the decision boundary would be different, but still is not converging to the model that you want. Maybe let's increase the number of layers. It got a little bit better, right? But not quite, right? And let's increase this number of layers. Try again to see whether it works or not. It is trying hard to find these decision boundaries, right? Still is not able to converge, give us the right model. Let's try this. Still the same, right? So how we can fix this? What do you think?
Could we have some kind of like transformation of the input data that would unswirl? I mean, I feel like we could only arrive at that solution by looking at it, and only in a situation where it's like simple enough to visualize.
Right, but then you use the intuition how the examples looks like, right? See, it is trying hard to find these boundaries, right? So it's getting there by making it a little bit more complex, right? And then, right, so here we wanted to really use the raw features. You could use this transformation as Cody mentioned, right? Let's maybe try them. You could use this transformation and see whether it finds anything there. See, it is converging faster than not using them, right? But you saw that sometimes maybe it's not really stable. But again, the more complex feature you use as your input, the more domain knowledge that you use for your training example, and probably this is not what you want to use, right? You want to use only raw features, and then let your complex network to find these nonlinearities in your data in order to classify these. So basically, this is a matter of try and error on different architecture, different nonlinearity, and so on. See, even we make it more complex with the sigmoid function, it is not really doing well, right? So here the choice of activation showed itself why it makes sense for certain models to use some sort of activation over other type of network. But this is a good good tool to use to learn about the interplay between activation, between the model complexity, between between the number of training epochs and so on in order to learn a reasonable classifier. And this problem, finding the right architecture, finding the right activation function, could be formulated as a learning problem itself, right? And there is active research in neural architecture search. Basically, it is a hot and very important area in machine learning where people try to formulate this, the kind of play that we did just now, to formulate it as a search problem and find the best architecture or the optimal architecture with the right parameters in order to do the learning task. Okay, let's stop here and then talk to you on Thursday. Bye.